All right. So yeah, first of all, thank you very much for to Luke and Ariel for the invitation and for providing us with some very good, interesting talks. So for those who don't know me, my name is Giovanni and I'm a PhD student at UNSW Sydney. And what I'll be talking about today is some of the recent work that I've done in collaboration with the people that you've seen on the screen recently in the post-inflationary scenario. Focusing on the mini clusters, what we call the minivoids, and very recently on axion streams. So the way I want to structure my talk is to look at the post-inflationary scenario in the cosmological timeline from the Pei-Queen phase transition very early in the universe until today, with a focus on axion helioscopes, which are the experiments that are aiming to detect dark matter axions. So in particular, I want to answer some of the following questions. First of all, given that we have to rely on simulations because an analytical treatment of this scenario is not treatable, how much of the timeline, first of all, can be covered with simulations? And most importantly, what is the largest source of uncertainty? Because as we will see, it's not possible to cover the entire timeline with simulations. So we have to make unfortunately, we have to make some approximations. We have some uncertainty due to some technical challenges, and this will affect the final results. So the final observable, that will be the axion signal. So in particular, we want to really, the real question is how detectable are dark matter axions in this scenario where we have mini clusters and this complicated substructure. And also, we might ask, can we distinguish a pre-inflationary scenario from a post-inflationary scenario for this reason? So I don't need to motivate really the QCD axion, but I just want to have a quick reminder that in the following, I will just talk about the QCD axion. So the axion does solve the strong CV problem. And I will be assuming the Pei-Queen model, where we have just an additional U1 symmetry, which is spontaneously broken, a very high energy scale. FA, but is also explicitly broken at the QCD phase transition. That's where we have the solution of the strong CV problem, and as a bonus, the axion can behave as a dark matter candidate. Now, I want to remind what are the main differences in between the post-inflationary scenario and the pre-inflationary scenario, because in cosmology they lead to completely different phenomenology. So the pre-inflationary scenario is very simple. Imagine that the phase transition happens before the end of inflation. And so inflation will blow up any of the causal patches, and our observable universe today consists of only one of those. So in this scenario, it's very simple to calculate the hydraulic abundance. I'm sure that most of you have seen this calculation or done it. So the only comment that I want to make here is that the hydraulic abundance cannot entirely be predicted because we have the dependence on the initial misalignment angle, which is in principle random. On the other hand, the post-inflationary scenario is more appealing because in principle it could predict the correct amount of dark matter axions or what is the axion dark matter mass. Here the phase transition happens after the end of inflation. What this means is that our observable universe today consists of many causal patches that were causally connected at the time of symmetry breaking. So in this scenario, we have a very highly homogeneous distribution that leads to the formation of topological defects. So we have cosmic strings forming at the Pei-Queen phase transition. We have domain walls that we seen in the past talk that form at the QCD phase transition. But importantly for this talk, we also have mini clusters that form because of order one spatial fluctuation in the energy density. So given the complexity of the scenario, as I mentioned at the beginning, we can only rely on numerical simulations, and providing here just a list of the some of the references in the last decade. I hope I've included all of them, but essentially there has been a huge development and improvement in this scenario, even though we still have some controversies and tensions between the results of these simulations. So I'm going to go straight to the goal of this timeline is just to detect the axion. So the standard axion dark matter experiment is a cavity, a helioscope. You can imagine this cylindrical empty container that aims to detect an oscillatory feature, which is the axion field. So we'll have a frequency, which is set by the axion mass up to very small corrections. But the signal will also have an amplitude, which is directly proportional to the local value of the energy density. Let's take, for example, the axion to photon coupling, which is the standard cavity design. But this applies in general to any type of coupling. So what the experiments will try to detect is a signal in the Fourier spectrum. And if we ignore any order 1 factors which are particular to the design of the experiment, or in this case, it might be the geometry, we have that the signal is always proportional to the coupling. So in this case, there's 2 powers of the coupling, coupling to photons in this case. There's a random phase factor due to the phase of the axion field. But more importantly, this signal will be proportional to the local density. So this will be interesting at the end when we discuss the minivoids and see how the signal will be suppressed based on the different values that the local density can take. Then there's an additional term that gives the line shape that you can see on the left plot, which is inherited by the speed distribution of axions in a dark matter halo. So I want to stress again that whatever I talk in the following will apply to any experiment that are aiming to detect dark matter axions. And this goes beyond the cavity design and also goes beyond the axion to photon coupling. So we have different several different techniques to find the axion, magnetic resonance, the electric haloscopes. And some of the experiments, as I said, use different couplings. What I will be talking in the next applies to every kind of experiments, because they all detect a signal which is proportional to the local density. So just to provide some context, here's the plot that you can see in any Axion talk from Kieran. I'm just focusing on a very narrow part of the parameter space, which if we zoom in, is essentially in between about 10 microelectron volt, or let's say a microelectron volt to a millielectron volt, where these cavities are really trying to probe the QCD axion line or the QCD axion band, depending on the different UV completion. And as you might imagine, the biggest challenge of these experiments is finding the right frequency. Once we assume that all of the axions make the dark matter, what is the right value of the mass or the frequency? But what I want to put emphasis on is the role of the amplitude, because once we have a signal, we or once the experiments start running, that the sensitivity of the coupling has dependence on inverse square root with the local energy density. So based on how much local density we have locally in our solar neighborhood, we are able to tell how much of the coupling we can exclude. And what the experiments usually assume is that they take the value of the energy density which is locally inferred on a scale which is 100 parsec. So in the presence of mini clusters, as I will say in the following, this assumption might need to be revisited, and maybe the coupling the exclusion band will shift. So how does a typical simulation looks like in the cosmological timeline? So at the very early time in the Pacheco phase transition, we have the formation of strings. We have a network of strings, which are very energetic and decay into massless axions. But then at the QCD phase transition, the axion mass turns on, and we have a formation of walls which are bounded by the strings, and they form a string wall network. And if the network is unstable, then this topological defects network will collapse entirely, leaving no relativistic axion field except for some regions which are called axions, which are oscillatons. They will form the seeds for mini clusters. And the overdensities here are so large that they can collapse before equality. So this snapshot is actually at matter radiation equality. And as you can tell, there are already many mini clusters that have formed. And then at the final simulation time, which is about redshift of 100, we have all these mini clusters have hierarchically merged through gravity into what we call mini-cluster halos, which are nothing but clusters or mini-clusters. But the end of the timeline, the timeline doesn't stop there. What is the fate of the mini-clusters after is that they are, as the galaxy forms after Z of 100, they are likely to encounter many stars and disrupt forming tidal streams. So in the last part of the talk, I will briefly mention what we're doing with the axion streams and how can this impact the axion signal. So let's look again at the timeline of the post-inflationary scenario, and I'm going to give a brief overview of what methods we use to do the simulation. So first of all, in the first period, when topological defects are present, we can do lattice simulations. In particular, we solve Klein-Gonod equation for a complex scalar field, and when the topological defects collapse, we can just solve it for the axion field, which is just a phase of the complex field. We can further continue the simulation with the Schrödinger-Poisson equation in the non-relativistic limit. And all this is done in public code Jackson's, which has been developed by Javier Redondo and Alex Vaquero a few years ago. And what is interesting is that we can continue the simulation by mapping our lattice configuration into an embodied set of particles. And we can use gadget 4 to continue the mini-cluster simulation. So the mini-cluster simulation is an embodied simulation where only gravity is dictating the dynamics. And in the final stage, unfortunately, we cannot strictly continue the same simulation, but we can use the information of the final time of the embodied simulation to perform some Monte Carlo simulations of the mini-cluster orbits, how they interact with stars, and how streams are forming. And this will be published, the code and hopefully the paper very soon. So I want to highlight that there's a gap in the lattice timeline, and this is related to the strings. So we cannot cover the entire dynamical range here of between the string formation and collapse. And this is because we have a multi-scale problem. We want to resolve the core of the strings, but at the same time, the horizon size physics, the inverse Abel scale. If we put some numbers in, by the time between the time that the string network forms and collapses, the separation of the FA and the inverse Abel increases quite a lot, and is usually represented by this logarithm factor, which is about 65 when the string network collapses. And what we can do with the simulations is reach a factor of 10 or so, and this can be done with either a uniform grid with as many points as you can, or with mesh refinement, as has been done a few years ago by Bushman et al. So this log factor will impact essentially all the properties of the network, how dense the network is, what is the emission spectrum into axions, and essentially it also parameterizes the tension of the strings, which increases as the separation of scale increases. So why am I talking about strings? Well, because modeling strings will be very crucial for the mini clusters, because it essentially provides an initial conditions for the mini clusters. So what we can do in our framework is to actually solve continuously, but only from a redshift of about 10 to the 16 to a redshift of 100, as I was saying before, in a continuous way with all the different methods. But unfortunately, we cannot cover the first part of the timeline where the strings are developing the scaling regime and they emit axions. So in the initial condition, we have several options to take. So first of all, we can just initialize the system right before the strings are supposed to collapse. But if we do it in this way, they will have a small string tension because they didn't have enough time to develop the right physical tension. There's a second method where we can artificially add string tension, and this was done by Claire and Moore a few years ago. Essentially, changing the UV theory, you can create a tunable tension, so you can artificially add more tension as if the strings were at the physical value. The third method is instead to simulate the Peccei-Quinn phase transition and just having the strings and massless axions, study the properties of the network, and more importantly the spectrum of axions, and emitted in axions, and then extrapolate the spectrum up until right before the strings collapse. And this was inspired by Gorgetto et al. Papers, where they found that with the extrapolation, the spectrum was IR, leading to a different prediction, even in the dark matter mass. So what happens is these three different methods are entirely different, and will set different initial conditions for the mini-clusters. And what you're looking at is the dimensional spectrum in the energy density fluctuations right when the topological defects collapse. And as you can see, these spectra are, they're telling us at what scales the mini-cluster seeds will appear, and at what scales the mini-cluster will develop, so what mass and what size. So these different methods give slightly different predictions. In particular, the indirect method, the blue line, is shifted to extremely large momenta, which means that the mini-cluster index in that case will form on much smaller scales, with smaller mass. I'm not going into any of the details here because I don't have much time, but I can refer you to Kenichi's and Jilur talks tomorrow. So let us get to the mini-clusters. So they are a smoking gun of the post-inflationary scenario. They are gravitationally bound structure that form just because of gravity, and have been studied for a long time for indirect detection, for example, for microlensing. But for direct detection, they are quite problematic because from simulations, what we can tell is that most of the axions will end up bound in these mini-clusters, and encountering these mini-clusters is the encounter rate is quite negligible. So this leaves an interesting question for direct detection: is are we capable to detect the dark matter axions if most of them are bound in these objects?
5 minutes, please.
Okay, thanks. And also the survival is uncertain because, as I said before, they could undergo tidal disruption as the galaxy forms. So this is how a typical embodied simulation looks like. As you can see the ref sheet up top. Just because of gravity, the mini-cluster seeds will start collapsing way before matter radiation equality, and then keep forming this hierarchical structure in larger and larger mini-cluster halos. And I also want to highlight the difference between the methods. So on the left side, you see the indirect method of Gorgetto and collaborators with an IR spectrum, and on the right hand side, you see the Moore-inspired simulation where we have added string tension. And I also highlight the different times, different redshifts, and the different scales. So you might expect that on the right hand side, you have mini-clusters that form way earlier and on larger scales. So the point I want to carry here is that the simulations are looking very different. The mini-clusters are looking very differently because of the initial conditions due to the string modeling. And quantitatively, this can be seen by the halo mass function, as you can tell in the blue line. So in the indirect method has many more mini-clusters and much smaller scales, smaller masses. And interestingly enough, the prediction from semi-analytical modeling and the simulation can lead to a very similar result. So the take-home message here is that there's a large variance between the methods of modeling the strings, which impact the mini-clusters. So this will have to be kept in mind for future works. So get to the minivoids. As you can see, there are large regions which are still sub-parsec, which is the size of these voids can be related to essentially the size of the horizon at the QCD phase transition. So given the question that I was arising before, we wanted to estimate, and we did this a year ago, how big these voids can become. So in here you can see mini void size function. We can tell how many voids at what radius we can find. So this is an analog of the halo mass function, but for voids. But more importantly, we want to tell how much density do they have. And what we see from from our simulation is that the minivoids can get to 7 to 8% of the average value of the energy density. So in this plot, you can see as a function of time, or redshift, the minivoid density as it goes with time, and it decreases. But it seems like to reach a constant value after a redshift of about 500. This is also confirmed by looking at the density profiles using the full particle information. We get a similar answer that about 10 or 8 to 10% of the average value is in the minivoids. So this seems to be also interestingly stable against the different methods. So despite the fact that we have different prediction in the halo mass function from the different string modeling, there seems to be a common trend in the action in the density in the voids. So you can see they all reach a similar value of about 8 to 10%. And this is also a common trend can also be found in the bound fraction. So calculating how many axions are inside the mini clusters just in number, which is about 70% at late time. So what is the worst case scenario? Remember the signal that we're trying to detect is proportional to the local density. And in voids, we have a suppression of a factor about 10. So in that case, the sensitivity of the coupling shifts by a factor 3 because we have a square root as well. And what this means is that if we're in the worst case scenario where we're sitting in a void that does not get filled up with additional energy because of tidal disruption, then all the constraints that we had from haloscope will have to be shifted upwards by a factor of 3. And in some cases, it means that the haloscope is not touching any of the QCD axion lines. However, that's not the end of the story. As I said, there's the galaxy forming, and then the mini cluster can undergo tidal disruption. And in the past years, there has been a huge improvement in this work by some of you in the audience as well. So what we've done is we try to estimate how much of the voids can be filled up by the tidal disrupted mini cluster by the streams. So what we've done is we calculated with a sort of Monte Carlo simulation how much energy can be injected into these mini clusters, and if there's enough energy that can strip them, then they can form streams. But these streams have really parsec size because of their length is really related to the velocity dispersion that was inherited by the mini cluster. So you don't expect to have these streams which are wrapping the galaxy, but they really concentrate in a very small volume. And so what we estimate is that, just to conclude, is that at any point in time, if we calculate what is the density in stream, the typical number of streams in the solar neighborhood, we find about 1,000 streams overlapping at any single point in space. And if we add up all their densities, then we get that they only make up 70% of about 60%, sorry, of the measured value, the local measured value of raw dark matter. So if we also add the background voids, then we get to roughly a 70% of what is estimated, which is just a suppression of a factor 1.2 in coupling instead of 3 as before. So in this case, the voids get filled up, and we have a higher chance of detecting axions. And finally, if we look at the spectrum, we should expect, if the integration time is long enough, we have enough frequency resolution to see the streams, which are very narrow because they have a small velocity dispersion, and the signal should be able to distinguish from a smooth Maxwellian distribution, which is just the black dotted line, from the actual post-inflationary prediction, which is the presence of voids plus these streams, which are just narrow lines. So I will leave you with my summary since I'm running out of time. And thank you.
Thanks for the nice talk. Is any question? Okay, David.
Hi. Thanks for the great talk, Giovanni. So just you described for the indirect method, if I'm understanding correctly, the mass of the mini clusters predicted by the indirect method is smaller, but they also form later. So does that mean that for the IR spectrum indirect method, I've got lighter and less dense mini clusters, whereas in the other cases, they're heavier and more dense. Is that true?
Yes, I think so. In that case, they form way later because the overdensity is not large enough. So you have, they're less dense and at smaller scales. So the spectrum is smaller in amplitude and is also shifted to larger K. So that's the prediction. Yeah.
So much worse news for indirect detection.
Yeah. So exactly. So we base the let me see. Yeah, it's worse for direct and indirect both. Yeah, for both.
Thanks.
Thank you.
We maybe have time for one more question.
I have a question.
Okay.
Yeah. So I would like to ask what's the typical size of the minivoids? You mentioned something like a parsec.
It's still sub-parsec. You can tell here the radius of the void, it gets up to 0.1 parsec, which is the size of the co-moving horizon at the QCD phase transition.
Right. Okay. Thanks.
Yeah, so
Okay,
they're
so
not
thanks
cosmic.
again.
They're not cosmic voids. They're really small.
Okay, so thanks again for the